Thank you, Gerard, for this kind introduction. Okay, so the objective of my talk today is to present you some basic research order modeling techniques based on modal analysis for poroelastic materials, which are known as porous material. And in fact, this is the first part of 2 lectures on these materials, which are a kind of different physics, and the second one will be given by Romain Rumpler from Catholic. So I'm Olivier Dazel from Laboratory d'Acoustique de l'Université du Mans and a member of the Institute of Acoustics graduate school, which is a kind of faculty in acoustics where we are doing both research and education in acoustics in Le Mans. Okay, so the topic of today, this is, as I said in my title, to introduce you reduced order models for porous materials. So the first part of my talk will be an introduction on what are porous materials and key ideas on their physics. Then a short reminder on CMS techniques, modal techniques, but I think several of you are familiar with that. And then how to extend this modal approach to porous materials. These materials, this is biphasic, dense materials with an internal fluid structure, interaction coupling, and generally these porous materials are linked to other structures, master structures, and then most of my talk and about this extension of techniques will be to how to enrich the modal basis. It will consist mainly in 1D example to show you the basic things. I will finish with 3D approaches, and then after Romain will complete my talk. So what are porous materials? This is porous structure, so which are saturated by air. So you have a skeleton. This skeleton, it can be foams, also bread, wools, and this is saturated by air. And these materials are used to control sound and vibration. Okay, why do we control sound and vibration? Because this material, they have in their physics lots of damping material. Okay, first of thing, I want to just show you a short introduction about this mechanism. So air, as you know, this is a fluid. First thing, but I think it's familiar for that. But this is a viscothermal fluid with viscous and thermal effects. When we are in that room, more or less we can neglect them because we are very far from the walls. And these effects, which are viscous and thermal, they are close to the boundary. When you are in a porous material with some microstructure, less than 1 millimeter, you can imagine that the boundaries are very close one to the other. So we have lots of dissipative mechanism in air coming from this viscous thermal effect, and also a part of dissipation from the structure of the pore. Here I have a kind of balance about the repartition of this mechanism in porous materials, but we can say that 75% is done by viscous effect in the fluid, remaining part with thermal effects in the fluid, and just a small part in the structure. Okay, and so they are used in the transport industry, also in buildings, and we can control sound with them. So first thing, so this is with a microstructure, but one thing that you have to forget, this is for noise control engineering to model them at the microscopic scale, because you have a really complex physics at the microscopic scale, and here this is just a 2D example. So it's not acoustics, viscothermal acoustics, but it's electromagnetism, but more or less this is the same. And then you see one example of the microstructural response of these materials at low frequency and high frequency. Okay, here the red part, this is the solid part, which is motionless, and the grayscale corresponds to the velocity of the fluid inside. And what you see here in this pattern is that it's very, very different at the low frequency range and high frequency range. This is due to that because at low frequency, we have this viscous depth, which is more important. And then you can see that the waves, acoustic waves, propagate at the microstructural level inside big networks of pores. Okay, so 2 different approach at 2 different response at 2 different frequency. And then we cannot model that if we have a full structure. So what we are doing is that we homogenize. Okay, and when we homogenize, we will determine some equivalent parameters. These equivalent parameters, so will be like I presented here. So this is some coefficient which depends on the frequency because of what I've said previously, and also they are complex to take into account damping. So when we look to this expression, so I can enter into the physics, but this is not the topics of today. But you see that we have frequency-dependent coefficient that will be the equivalent. So here, this is the density of the material for the fluid phase, so for the fluid inside the pores, and you see this expression, which is, let's say, known and which is also very used, often used. This is the Johnson model. Okay, so now if we look to the modeling, so when we homogenize the porous material at the mesoscopic scale, so this material, which is diphasic, is modeled as the superposition of a solid phase and a fluid phase. Okay, so this is like when we homogenize the acoustic air, which is just particles, and we homogenize that. So here, for porous material, we have two continuum media that are coupled one to the other. And then, based on this homogenization, there are several formulations, okay? The most known way is the bio formulation that was formalized in the 1950s. So this is a formulation when there was the displacement of the solid phase and the displacement of the fluid phase as fields of representation. Okay, another theory done a few years after, and I will focus on some in my presentation on more recent formulation, one for which we have the displacement of the solid and the pressure as primary variables, and another one with the solid displacement and the total displacement. Total displacement is closely linked to the fluid displacement. It's not totally equal, but at least formulas are better. It's more easy to use this formulation. So what happens in this medium? So in one medium, when you have one medium, what you are interested in to catch the physics, this is what are the waves that propagate in that medium. So for a fluid, you have a compressional wave. For a solid, isotropic solid, you have compressional waves and shear waves. In a porous materials, which is a mix between a solid and a fluid phase, you will have two compressional waves and one shear waves. I will explain that after presenting the model in a couple of minutes. And on this physics, you can use a lot of numerical schemes, so analytical methods, transfer matrix method, finite element, wave-based methods, and some others. Discontinuous Galerkin, the list is not complete here. Okay, and this will be our full order model. Okay, so now, yes, one comment is that the porous material generates a small structure linked to a master structure, and then it's bigger structure, but you need to put a lot of degrees of freedom in this porous structure because they control damping. So that's why sometimes this is the analogy with this GO and the B on the GO. So what are these formulations, my full order model? So one first example, which is perhaps the most easiest one to catch for people from structural dynamics, this is the displacement formulation. For that, it's solid displacement and the total displacement. And then we use that as primary variable of our finite element model. And then if you see the system that you have is that you have stiffness matrix and mass matrix. In this stiffness matrix, you can see that so we have some coefficient here with all the tildes are parameters that depend on frequency. And then you see that in this formulation, you have this mass matrix with 4 times the same shape matrix M0 multiplied by this coefficient. This coefficient came from the Biot equation. It's not necessary to know them by heart, but yes, this comes from the Biot equation. Okay, and for the stiffness part, so we have 2 parts, one which is associated to compression and another one which is associated to shear. Okay, so at least we can say that we have a stiffness matrix and a mass matrix, but they have a size which is twice the size of the classical things that you can have in elasticity. You don't have shear waves in the fluid phase because the fluid does not restore shearing stress. Okay, and then you can discretize that with finite element. So this comes from classical finite element, and you can also use higher order elements, but it's by classical techniques. Okay, so that's displacement formulation. And for that, we have 6 degrees of freedom by node, because for one node, we have free displacement for the solid, free displacement for the fluid. So, second formulation, what is called the mixed UP formulation. In that case, because the fluid does not restore shearing phase, we don't really need the total displacement, but the pressure and the gradient of pressure is sufficient. Okay, so for that, you have what is called the mixed formulation. Okay, and the difference between the mixed formulation is that we keep the displacement of the solid phase and we replace the total displacement by the pressure. Okay, this means that we have 4 degrees of freedom by node. Okay, you have a classical term here, which is just the one associated to the solid part, one which is similar to the fluid part, to a classical fluid problem, except that we have this frequency-dependent coefficient, and also a coupling matrix. And this is not a coupling matrix of fluid structure, it's just because this is in the volume that we have the coupling between the pressure and the displacement. Okay? If you want to make the full order model, you have a mesh which is controlled by the shear wave, because this is the one with the lowest wavelengths, and frequency complex coefficient. We have these matrices which are presented there. And also one thing, which is that in this formulation, which is symmetric, you can see that we have omega square, which is at the numerator for the solid part, and at the denominator for the fluid part. So once more, influence of frequency, which is a bit. So when I've done that, so this is my full order model, okay, my 2 formulations that I have introduced. So based on that, I need to spend 3 or 4 minutes to discuss about the physics of these materials. So I said that there is 2 compressional waves and 1 shear wave in the porous material. To obtain that, what we are doing, this is quite classical in physics, so we make dispersion analysis, we look to the fundamental solution, which are plane waves. And if we look in the displacement formulation, we have a problem which is like this. Okay, so in which we have the displacement of the solid, displacement of the fluid. And when we are looking to possible plane wave, we determine that we have, in fact, 2 solutions, okay, which are numbered by this delta. So we use delta because Bio use delta, and this delta, this is the wave number, which is usually represented by K, but because we have the density, which is also modeled by K, we prefer to use delta, okay? But delta, this is the wave number. Okay, so you can see that we can obtain analytically the wave number, and then we have 2 compressional waves because we have a quadratic problem. And associated to the eigenvalue, we have a ratio which is mu, and this ratio, this is just for one wave, the ratio of the total displacement over the solid displacement. Because in the porous materials, because this is coupled, we have a wave which is propagating in both medium, in the solid and in the fluid. And mu control the ratio between both. So when we do that, just one example on a, let's say, classical foam about the wave numbers. So I put the celerity and the imaginary part, so just for convenience. And so we see that I have in solid line my 2 values as function of frequency. Okay, and then so I plotted in dashed line the velocity of the compressional wave in the in-vacuo solid and also in the equivalent fluid. Equivalent fluid, this is just the solid is not moving, so you just have motion in the solid. So you see that in my 2 Bio waves, I have a similarity and I have a wave which is close to the one of the solid when there is no fluid, and one which is close to the one of the fluid when the solid is not moving, the equivalent fluid. So we see that we have these 2 waves, and the difference between both, this is just due to the coupling in the real porous material. And we can identify these 2 ones. And in the second thing, what we find is that the one associated to the fluid has more damping than the one associated to the solid, okay, which is close to what I said before, that 75 or 80% of the dissipation is in the fluid, okay? Another one, this is to analyze this ratio mu, okay, which is the ratio between displacement, total displacement, so let's say displacement in the fluid and displacement in the solid. And you see that for the solid wave, the one that was identified previously, we have that more or less the ratio, this is in red, this is equal to 1, and the phase is, let's say, equal to 0. which means that for the solid wave, the solid phase and the fluid phase, they move in phase more or less are the same. And for the other one, we see that the fluid is moving a lot. Then we have that the solid move less because we have a ratio around 6. And also this is in opposite phase. So lot of difference of velocity between the two phases. Okay, it was important because you will see that it will come also these physical aspects in my presentation. Okay, you can play with poroelastic materials or have more information on that because I give a full course on this in a summer school. So you have the link here, and also we design a small tool to control the absorption of it. If I present that, this is just to show you a typical absorption curve. We want this material to absorb energy. So here, this is the absorption coefficient as function of frequency. And then you see that the response of a porous material is something that is generally growing with frequency. Okay, the problem is low frequency when we have a weak absorption. And we can say more or less that around 100 or 1,700, we have a maximum of absorption. This corresponds to the quarter wavelength resonance of the fluid phase. And also you can see that around 1,000 Hertz, I have a kind of decrease in my absorption. Why do I have that? Because here this corresponds to the quarter wavelength of resonance of the fluid. And then at the quarter wavelength of the fluid, you have then the two motion working in phase, so less viscous effect, then a decrease in the absorption. Okay, just I don't take too much time to present that, okay, but at least you can have more details. And I think you have the necessary elements to follow the rest. So now the idea, as we have presented the physics of this material, this is to come back on reduced order model. So to do that, just in one slide, I remind you very quickly what are these reduced order model. So we focus on modal reduced order model. So you have a classical full order model with mass matrix, stiffness matrix, and you see here, because my coefficient depend on frequency, that I put them out from the matrix here in this example. Okay, but at least we have M0 and K0. This is classical matrix, symmetric, positive definite, if there is no rigid body mode. And of course, we have decoupling of the modes classically. So the idea, this is instead of considering the physical coordinate, this is to consider the modal coordinate, and then to use this decoupling to determine this contribution of the different modes. Okay, when we do that, we have decoupled equation. Okay, so instead of solving a full problem, we have a decoupled problem, so simple scalar equation, and we can solve this very easily. You see here that the formalism that I choose is a bit different than the one that you can find in structural mechanics books, okay, but because this is also linked to the physics that I presented, but this is the same equation. Okay, you have decoupled equation in a formalism a bit different, and what you are doing generally, this is a truncation to reduce your model. Okay, so instead of having a big N size of the system, you have less coordinate. Okay, fair enough. So if we see that on one example, so here, this is just a simple acoustic problem of a tube with an imposed velocity. Okay, you have the measurement, your full order model that fixed to the measurement, and then you want to reduce your model, and then you choose 3 modes. And then what you see, this is an answer like this, where we can see that at 3 frequency corresponding to the resonance of the tube, you have a good approximation, and in between, this is not so satisfactory. Why is that? Because we neglect in the sum a huge number of modes. So if we go a bit in details, you can see here, this is the shape at the anti-resonance. Okay, so this is the second anti-resonance. So this is, and then here, what you can see is that in blue, I have my full order model, and in red, I have my reduced order model with 3 modes. Okay. And what we see is that we have an answer which is not so good, and because in the mode that you selected, because the mode depends on the boundary condition, and here we use it's acoustic, so rigid modes, then we have some modes, we can say with a 0 slope, and then when you consider these three modes which are presented here, so one which is constant associated to the rigid body modes and the two first mode, two first elastic mode, we see that we have a problem at the force. So to fix that problem, the idea this is to do enrichment. To do enrichment, how do we proceed? In fact, if I look to my full modal basis, I have the modes which are in red, which are the ones that I keep, okay? And we have in blue the modes which are neglected, okay? So I can write this is formally equivalent. And for the mode that we are neglected, the point is that we can see that this contribution, if you have a given spectrum of excitation, if you select some mode, the one that you neglected, more or less, they work in their static regime, okay? Because you see on this example that on your spectrum on your spectrum of excitation, then you can, if you have a static response, you can more or less not to have the individual contribution of the mode, but you can at least have some vector that you can use to enrich your basis. Okay? So this is the principle. And when we do that on this example, so we have this additional mode, which is in green here, and we add it to the basis. And then you can see that on my shape, I have a better answer. And then I fix my problem on the on my impedance. Okay. So here you see that we have perfect, very good response at the anti-resonance because I enriched that. And so the idea now, this is how to apply that to the porous material. So first, a simple case. So this is beads materials, and for beads materials, so this is a porous material, okay, but because this is beads, we don't have shear, let's say, in the solid phase. Okay, so when I come back to my model in displacement formulation, there is one term that I can split. So I have a stiffness matrix, K0, mass matrix, and then I can use this matrix as modal form to reconstruct my modal basis. If I do that, this is my full order model. I have some modes associated to K0 and M0 matrix, which are of half size compared to the full order model. So I compare them, everything works. And then when I am in the modal basis, you see that I have my diagonal matrices arriving there. So here, what I have, this is the modal contribution for the solid and the total displacement, okay? But you see that these equations are not totally decoupled because they work by pairs. Okay, for one model shape, we have a contribution for the solid and for the total displacement, and this is two equations, okay, which are coupled equations. Okay, and this we can solve them analytically. And when we solve them analytically, what we have is that we have an expression that each contribution is a sum of contribution that can be written in the similar form that I used previously, associated to the. And if we look to that, so for example, the contribution, this is the sum of something that I will call a polar function. This polar function is the one getting the resonance. It depends on the geometry, and we generate also the resonance with the wave number of the Biot waves. Okay, so that's why also I change a little bit the formalism, but so we can extend that, and we have some function with two resonance. If we enter into the detail of this function, you see that, for example, on the left, I have the absolute value of the polar function. And then we have one associated to the solid. You see that this one associated to the solid has a resonance which is quite important because the solid no so much damping, and one associated to the fluid, which is smaller resonance, but associated to the damping as well. Okay, so you see that analytically we can do that. And then the idea, this is how to, because we need to enrich also this basis, so how do we proceed? To proceed like this, we can just adapt the methodology that I presented before. Okay, so we look to, this is the contribution here for the solid or the total displacement. So we have the preserved norm, the one that we keep, and we have the other one that we want to create a kind of attachment modes to enrich my basis. And for this mode, the idea this is to use the static response. To do the static response, of course, the idea this is not to compute this mode. So how do we proceed? I just show you how to proceed. We calculate a static response of the full order model. From that, we determine the one of the modes. We add we subtract the contribution of the modes that we have kept. And what we have, this is the sum of the contribution of the modes that we have previously. This is this psi. So this psi, we don't need to know all the non-kept mode. We just need to, what we want, this is the sum. And this can help to enrich our basis. So if we do that, an example, simple example, 1D. If we do that, so here I have an example with two porous materials. So the first one, this is a foam, and the second one, this is a fibrous material. Okay? And here I am at 150 Hertz. Okay, and I plot what is the total displacement. Okay. Why the total displacement? It's because this is the displacement of the fluid, and in this problem, we have a fluid in a porous material, something that I didn't say, I have a very short presentation. A porous material, this is 98% of air. That's why it's very light. Okay, glass wool and glass, this is, we have totally different density. So here in that material, when we excite just a porous material, what we mainly excite, this is what happens in air. Okay, and the total displacement is linked to air. Okay, so I have my melamine, 2.5 centimeter, and here this is my total displacement. So first strategy, no enrichment at all. So for that, I keep the minimum modal shape for both structures. Okay? What are the minimum modal shape? Is that for the first foam, I have two modes. The first one, this is the rigid body mode, because here you see that with this structure, we have a rigid body mode. And the second one, and then we take a rigid body mode and an elastic mode. And for the fibrous, there is no rigid body mode, so just one elastic mode. If we do that, we use just this mode, we have this response, which is in black. So in black, what do we see? So we see that for the foam, we have the rigid body mode, which is a kind of offset also, and the first mode of this, which is just a rigid mode, which is just half of a sun. And for the fibers, we have zero displacement due to boundary condition, and then a free condition, which means that, in fact, the derivative is equal to zero. Okay? So what I want, this is to have this blue curve, and with my model basis at the minimum, what do I have? Is just that because I have a zero slope for my two modes, then what I have is that you see that when I can couple them, but at least this creates a kind of torsion of my answer. And then a wrong thing on the left side of my ports. So to enrich, classical thing of fluid structure, we enrich, we create an attachment mode with the methodology that I present by putting kind of additional force on both sides. And by doing that, so this is the classical CMS approach, then we see that at least at the interface between the two materials, we have a better displacement. On the left, this is very important because this is what will generate the interaction with the external fluid. You see that because we have also this first mode, which has a zero slope, in fact, we don't have a satisfying response. But for that, the solution is quite easy. We need to enrich this by adding another attachment mode on the left. Okay? And as a summary, we can say that for this 1D problem, with these two problems, okay, we have an absorption curve, which is modeled like this. So the analytical response, which is in blue, so this is the exact response, that is exactly the same one, the full order model. If you don't enrich, in fact, you see that you have poor prediction of your absorption. Okay, you have a poor prediction because the modes that you use are not perfect enough. You can correct that if you create attachment modes and if you enrich at your interface. And it's necessary if you want to have a good response to enrich also by taking into account to enrich at the interaction between them. Okay, so this is the spirit, and so this is a first example. Okay, what happens now for a more complex problem when we are in 3D and when we couple this porous material to, let's say, an acoustic cavity? Okay, so here, if we look to the full order model, this is composed of several parts. The first part, this is the one associated to the air cavity. So you have an air cavity, excitation on the air cavity, and a porous material. So if we look, we have a first part, which is in blue. So this is classical finite element formulation for a fluid. We have in red formulation for the porous material, okay? And you see that we couple them by Lagrange multiplier. Why? This is to have separate substructures that are coupled by the Lagrange multiplier. Okay, so this is my full order model. And then for that, if I analyze, so this time I have everything in the physics, and then I can exhibit three modal bases. The first one, this is for the fluid or air. Okay, so this is associated to HA and QA matrix. One associated to the solid part of the porous materials with K and N, and one associated to the fluid part of the porous material. Okay, so I have three systems, and then the cavity and the porous, they are linked between Lagrange multiplier, and the solid and fluid phase, they are linked by this coupling matrix of the UP formulation. So this volumic coupling between the solid and fluid phase. Okay, by doing that, if we now go into more detail, we can say that we have some modes, and then when we project the system on the acoustic mode, we have a system which is like that. So it's diagonal because I used this, and also we can say that by keeping and by neglecting the second term, we are just looking to the static response of the non-preserved mode. Okay, so what I'm doing here, it's formally and algebraically what I presented before. In practice, we use the trick that I presented before, but to do the algebraic development that I will present, okay, I keep this term. But this is exactly what I done. So by doing and suppressing this term, I neglect the dynamic response of the fluid modes. We can do the same for the porous material, but for the porous material, it's more tricky. For the solid part, so you have diagonal matrix, which are, I have a pointer, but okay, so this is this part, these are diagonal. By doing that, I neglect dynamic response, so keeping the static response. And here, this is for the fluid part. So all that part, this is diagonal. Okay, and because I have this internal coupling, okay, what I create when I project this coupling matrix on my mode, what I neglect, this is what I have here. This is a fully populated matrix. Okay, generally, we don't like to do that. So how to handle with that? Because this is good, this is diagonal, but this is fully populated. So what we are doing is something which is that in the physics, there is a dissimilarity between the fluid and the solid phase. As I presented before, the fluid phase has not the strength to excite too much the solid phase. So what we will do is that we will neglect this term, okay, corresponding to the excitation of the fluid phase or the neglected mode of the solid of the fluid phase on the solid part. By doing this, okay, so we are doing this classical approximation to suppress that term, and also I neglect this one. Okay, we have tested that several times on the full order model, and this is a very reasonable assumption. And when we are at that step, with all I presented, everything that I will derive now will be just exact. Okay, so my only assumption that I take, this is to neglect dynamic part of higher order modes and disturb. Because when we do that, and when I focus on this part, we can write, for example, we can first write that the pressure, so this is the mode that I kept, and this is the contribution of the higher mode that I will call pH. And because here I have the frequency dependence that are clearly exhibited, what I can write is that this pH is in fact this rho omega square multiplied by something which is composed of three terms. The first term, this is an attachment associated to the force. The second one is associated to the coupling, because we have the gamma. And this is the attachment mode associated to the neglected term of the solid phase, which are taken here in that matrix, and another one associated to the coupling of the porous with air. Okay, so this is, let's say, quite technical. Okay, when I give this the full presentation of that to some doctoral student at Le Mans, it takes 1 day about all of this. So you can imagine that in one side you don't have the detail. But just the key point of my presentation and what I want to say to you that is that with linear algebra and by combining all this equation, we can enhance and enrich the basis with all these terms associated to different contribution of the inside the pores. Once we have done that, we follow the linear algebra calculus, and we can create similar basis for the displacement on the solid and the full displacement of the fluid. And then we can enrich the basis later. And as I said, everything that I've done after my simplification is exact. So we enrich with a lot of additional terms. Okay. Then let's now do some example. Yes, I have 5 minutes if we want to have time for question. So yes, some classical benchmark that we are doing. So, and you are using the same benchmark, more or less. It's not exactly the same, but similar benchmark. So this is the one that we use in the community. And the first one, this is the classical cone tube. Okay, so you have an air cavity with imposed velocity and then a rigid body. Okay, and the porous material is in sliding condition. For that, this is, we can model in 3D, but this is a 1D problem. Okay, and then we model it in 3D, create this, and what we have, just is that here, this is the pressure in the cavity. So I take a zero reference because this is in dB, so at a zero frequency. And then, so you can see here that what I want to, the exact response is the one which is in red, so here. So here you can see the influence of the porous material, which is to create damping. For example, if you compare to undamped cavity, so when you replace the porous material by, or you suppress this dissipative term in your porous material, you see that this is the influence of your porous materials, adding damping to the thing. Okay, we can also use a model which is to neglect the solid part. So this is an equivalent or a fluid model. So you see that we don't predict exactly, but here we have this bio effect that we see previously on the absorption coefficient. And then we can highly model this with the model technique. And if we enter into the detail, we can have a good approximation with 6 modes in the cavity, 1 mode in the solid, and 2 modes for the fluid. Okay, so, and with all this. And in terms of computational time, so it's some old results. I think that now if I run on modern server, the time reduced, but at least the ratio remains valid. So we can at least reduce the computational time for from a ratio which is around 10. And also we have something which is more efficient than the one where the porous material is modeled as a fluid, so less degrees of fluid. Okay, so at least we have a gain and we validate this this method. Another example, you have a similar in your presentation later, is that so we have a smaller cavity. We excite on one point to have some shear effects, and once more, I will go a bit fast, but we reduce the computational time with a ratio which is around 10. Okay, so for that, what is done is that we use the normal modes, we enrich the things, and one thing is also that you can see that to create this additional form, you do it just once, because this is a calculation which is done at, let's say, the 0 frequency. So if you multiply the frequency by 10, you just increase the time of the frequency loop. And one thing is also that the time to compute the modes here is quite important, but yes, it's also due to the effect. So another example, which is on a non-Cartesian geometry, so which is purely 3D. Okay, so for that we use similarly exa27 element, and we have a more important computational time also by using the link model, which does not take into account the solid effects in the geometry. Okay, so here you have the pressure. And also, you see that with the porous materials, you dump some modes of the cavity. If we look to this, and if we want also to, so Romain will present you selection of modes. Here in that result, we were mainly working on the strategy. So we increase mode by mode, okay? And so the first thing to do this is to have some modes in the cavity, okay? Yes, because this is the cavity that governs the dynamics, okay? The porous is just having some damping. And you can see that by keeping just few modes in the poroelastic part, one mode in the solid and one mode in the fluid, at least you can have a good approximation of your frequency in the cavity. So which is quite good, but sometimes when doing numerics, we want some very accurate response. So in fact, if we want to reduce the error, we need to increase number of modes, and especially increase the number of modes in the solid phase. Okay, because this is for that you see that we can reduce the things, and where we have the bioeffects. And when we do that, we obtain something which is that for the solid phase and the fluid phase, because also we have these shear effects, this solid phase comes into this, let's say, mid-frequency regime where the modal density increase at lower frequency than the fluid phase. What does it mean? It means also that this is one of the limitations of this modal approach, is that at some moment, with modes, you can reduce things, but when the modal density is too important, even if you enrich and you control your thing, what you can do is not accurate because you need more modes. And also, you have the uncertainties on the parameters, so more or less, there is no use to do modal techniques at that point. But at least we have made our job to have the method as efficient as we want. So at least when we compare what we see, we have this resonance in the solid, but we can at least decrease from very important things for a ratio of 20, the computational time. Okay, so this was to show you on and now I think that I'm more or less okay with my time. Okay, so one thing about the conclusion. So what I've presented here, so this is the physics of the porous material and how to extend the modal approaches to poroelastic material, and mainly based on enrichment by attachment modes or classical CMS techniques that are. One important thing is that in this work, you have seen that also we try to link the numerics and the physics, okay, to put the analytical expansion as much as we can. And of course, these methods are limited, but this is the classical limitation of porous materials, and especially because we have a modal density of the solid phase that, yes, the solid phase comes into this mid-frequency regime very early. Okay, so this is some results, which was also to show you that for different physics, okay, we can adapt classical techniques. But for that, what we need, this is to have a good insight on the physics that you model, and also a good insight on the reduced order modal. One thing that we developed later was to go to some discontinuous Galerkin methods, okay, to use yes to overcome this limit of the low frequency limit for this solid phase. But this is another story. And then perhaps this will be the objective of next lecture in the future. Okay, so I thank you for your attention, and I'm open if you have questions.